righty. So all we need to do is finish chapter 17, and we're done. Oh, it's a tough thing. You guys are dragging. I think teachers are dragging at the end of the semester. So actually, this is a review slide. And we talked about the Big Bang in chapter, actually, we are talking about the Big Bang here. We're talking about dark matter, dark energy in chapter 18. Chapter 17 talks about the Big Bang. So it's like two things that we can still observe today. Test question. And those would be the thing we talked about on Friday, that the Wilkerson and, I can't think of the other guy, but they saw the kind of the hiss from the Big Bang with their radio telescope. And then the other one we're going to talk about today is kind of how much, when we look at the different elements in the universe, especially the early universe, what sort of proportion is there? And so that's the second one. So this right here is this isn't what Wilkerson and, dang it, I can't think of his other last name. But this isn't the map that they came up with, but this actually is a refined look at the energy coming from the universe some 380,000 years after the Big Bang. So the W map, you guys don't have this slide, but WMAP actually is a spacecraft by NASA, and it looks like this. So the picture you just saw of the baby universe was put together by this. And the video we saw on Friday kind of definitely talked about that. I was really struck by the video because it talked about how did they get this satellite in orbit to take that cool picture of the cosmic microwave background. And so you can kind of see the red is the trajectory of that little gizmo. It's so adorable. It actually left Earth, kind of circled Earth a few times, and then slung around the moon to get some gravity energy from the moon. And it's kind of cool. Anytime a spacecraft does that, slings around a planet or a moon like that, it actually steals some of its energy. It's pretty fun. And then it's slung out here to a stable Lagrange point. Now, we've actually heard the word Lagrange before when we talked about one of the locations for, test question, for asteroids in our solar system is to kind of escort Jupiter around. And those places ahead of Jupiter and behind Jupiter as Jupiter orbits the sun, those are Lagrange places, stable Lagrange points. So the L here stands for Lagrange points, but associated with the Earth. And so actually then, and I didn't know this, sometimes when I'm teaching, I'm like, oh, now how does that work? So I went and chased it down a little bit. So here, of course, you see the sun, and this is the Earth. And so then this little WMAP, it kind of orbits kind of a Lagrange place outside on the other side of Earth. Isn't that so cool? So it just kind of is hanging out there, which makes sense because it does not want interference from the sun, does not want interference from the Earth. So it's kind of headed out the other direction. I just think that's neat. And then that reminded me of this. Okay, and I was like, they're both gold. This is a different spacecraft. This is a spacecraft, I've talked about New Horizons before. And New Horizons was just in the news this week. That cute little spacecraft is waking up now, getting ready to get some great pictures of Pluto. And this actually is an old article put out by the BBC, but I thought this was adorable. So that's New Horizons, and look what they named everything. Alice, Ralph, Lori, you know. It's adorable, right? Those astrophysicists,
but then why do they
have so much fun.
Pepsi?
I know, so that's not fun,
No,
okay?
I know, right?
But I like this caption because it says what they're going to talk about, or what this spacecraft is going to do, that is waking up on its way to Pluto. I think it's July 2015, so it's coming up. So far, so good. So that has nothing to do with, okay. All right, so the second of two things that we can actually observe today that says, hey, this whole idea of those 8 eras I think we talked about on Wednesday's lecture, those really are the real deal. The second of two is how much hydrogen and helium are there, relatively speaking, in the universe, or especially the younger universe. So hydrogen is simpler than helium. Hydrogen is simpler than helium. So helium has to be constructed by kind of hydrogen is one way to think of it. So this is trying to kind of show you why we should expect early on in the universe to have much more hydrogen then it's more complicated helium. We should run about a 3-to-1 relative amounts, and that is what they see, and it makes sense. Okay. So this is a little more complicated. Look at not just hydrogen and helium, but also lithium is up here. And it just, and I had to study it at my desk a little bit, but if you just kind of focus on this gray area right here, okay, this gray area, okay, corresponds to about 4% normal matter. What's the opposite of normal matter? Dark matter. Most likely candidate, those weakly interactive massive particles, those WIMPs. Okay, so actually what we observe with regard to lithium, let's see, the blue one, let's see, okay, they all kind of match up. So again, we're kind of on track with regard to anticipating what is. It's always nice when the data supports what you observe. Okay, so there's a lot of things not yet explained, or in my mind. It's explained to astrophysicists, which is way over my mind. But one of the things that so far in lecture we haven't necessarily addressed is, for instance, the structure of our universe that we know to be kind of galaxies in clusters and clusters of galaxies and superclusters, and they're kind of on walls, kind of in filaments around large things, regions we call voids. I mean, how did that get to be as it is? Okay. Well, if we introduce something called inflation, and I mentioned this on Wednesday. One of the eras on Wednesday we talked about was the gut era. Okay, good. Okay, actually it stands for an era that was transitioning where 3 of the 4 main forces were together, the gut force. Okay, but somewhere around there, and preceding that time when our universe became transparent was a time called inflation. And the video we watched on Friday talked about inflation. Do you remember? And it caught my ear because he's like basically the universe was not only expanding, but it expanded at a rate that is faster than the speed of light. So literally it went from here to here faster than the speed of light. Okay, that's inflation. Okay. And I kind of told you, if you think of a balloon, you're blowing up a balloon. So a dramatic inflation of our universe. So how that enters in, I'll show you here in a minute with regard to that background, that cosmic microwave background noise we see on our cosmological horizon. But this is trying to kind of show you the all at once, okay, where basically over here where it's small, okay, this would be t is equal to 0. And this is almost t is equal to 0. So in basically no time at all, it went, all right? So one of the things that happened is, I don't know if you can see them, but there's like little, well, you can start to kind of see them here. There's little irregularities. Okay, this would be the fabric of space and time getting larger. Okay? Those kind of little irregularities were important. And actually those little irregularities before inflation existed after inflation, and those little irregularities are going to become our galaxies, quite frankly. Okay, so inflation is important, and it makes sense as to what we see today. Those kind of little, we're going to call them seeds here in a minute, those little bumps. So without inflation, and you know, you might have to kind of put this under your pillow or think about it, but without inflation, it's hard to imagine why when we look at the cosmic microwave background, why is it the same all the way around? Okay, what that would kind of suggest is we are kind of like in the middle of where the expansion occurred. Okay, and we aren't that special. But when we look all the way around, we see this cosmic microwave background. Okay, and how did it get there if we all were kind of one blob and we've expanded? Why isn't it some here and nothing there? Okay, why is it all the way around? So this actually kind of introduces you to inflation. And I do have a little video to show you. But so up there is where we are today. By the way, you see that magical time after the Big Bang, that 380,000 years after the Big Bang. That's actually, remember, begins with the era of atoms, where electrons finally said, okay, all settle down and all become part of an atom with a nucleus, okay? That actually was important so that energy could kind of go ahead and start headed our way with regard to seeing things. The universe became transparent. So here's the deal. Down here would be singularity, where all of the energy and matter and the fabric of our universe, fabric of space and time, was all one little dot, okay? So it began to unfold, and along here, along the y-axis, you see time. So a lot happened in the first part of a second. We talked about that on Wednesday, okay? This would be the period of inflation, okay? And then after inflation, of course, we have the accelerating, expanding universe, expanding the universe that is expanding, and its expansion is accelerating, okay, ever since. So this would be inflation, where the physical size of our universe went from being like this to being like this, okay? And it's been expanding ever since. So let me go ahead and play this little animation, which basically does what this figure does. It's a good one. So this talks about density. Now, density is different than mass, because a while back in the end of chapter 18, when we talked about the 4 different scenarios for our universe, was our universe going to recollapse? Quiz question today, right? Was our universe going to go ahead and just kind of stay the same size? Was our universe going to kind of coast with regard to its expansion? Or is the expansion of our universe accelerating? It's that third one. Okay, we talked about critical mass. But this is talking about density, and density is kind of the distribution of mass. Okay, if an object is dense, it's basically got all its mass in a small volume. If it's not dense, it's got its mass kind of spread out. So we have these, does this look like the fabric of space and time? It is. So that's like the fabric of our universe. Our universe could be flat. If we're basically running a density that's right critical, I always think of Goldilocks and the 3 bears, just right, okay? If our density is greater than critical, we're going to kind of have this spherical sort of fabric of space and time. Less than critical density, we're going to kind of have this saddle. Okay, but anyway, I don't have a whole lot more to add to that, other than it looks like our universe is flat. Okay, so that would fall under the scenario of we are right about critical density. But this points out, depending upon your size and kind of the magnitude of the space you're walking around in, what is really spherical might appear to be flat, if you're an ant, for instance. Okay, so this again is actually looking at, wake up, okay? Harley, wake up. This map is again looking at the cosmic microwave background, and those little kind of seeds there, we're going to call them, actually we call them here. They weren't always observed. When they first came up with this map, it was just like one homogeneous look at it. And then it was that WMAP, NASA's cute little gold thing, satellite, that actually started to kind of see some texture in it. Okay, so those are cute little seeds. They didn't always know that were there. This actually is kind of a distribution of those seeds. And like I said, those seeds are important, those irregularities were important to grow galaxies, basically. Okay, so here are some figures. I was looking at this in my office kind of thinking, now how does that work? So if you're like me, you like to kind of look at percents and kind of say, add them together and see if they make 100%. But these are numbers that we've actually seen before, where actually if we look at the amount of total matter, okay, the total matter is actually the baronic matter, which is normal matter, okay, plus the dark matter, okay, total matter. And so actually, though, if we kind of look as matter being interchangeable with energy, Okay, we've got a lot of energy in our universe that's dark energy. And the other thing that we've kind of come back to, remember that the Hubble law said that the age of the universe, the time from the Big Bang, was running about 13 to 15 billion years. Okay, we end up dating the universe an independent way. Okay, independently about 3.7 billion years. Okay, and then down here, again, if you're a cosmologist, a branch of astrophysics, you actually would say WIMPs, those weakly interactive massive particles, are a player when it comes to creating the universe as we know it. Okay, so the last topic is this, Olber's paradox. And I'm like, well, what is a paradox? Well, paradox is kind of like you think it should be this way, but it's really this way. I guess, I don't know. But if we start with a premise, okay, that if the universe is infinite, now an infinite universe is opposite of what I've been describing. An infinite universe is opposite of the phenomenon that physicists call the Big Bang. Because an infinite universe says that there wasn't any initial, it just was infinitely. Okay? From what we know, if the universe is infinite and if the universe is unchanging and the universe is the same everywhere, then quite honestly, we should be, and I'll play a video to try to kind of show you from Minute Physics, we should basically see stars cover the sky. Okay? We see a lot of stars if you're in a dark location, but they by no means cover the entire sky. So this is to say, basically, then the premise, the three premises, that we live in a universe that's infinite, unchanging, and our universe is everywhere the same, then there must be something wrong with that premise. Okay. So here's what that looks like. So we can kind of liken the sky being filled with stars as to being in a forest that is crowded with trees. Okay? So in this case, if you're in the middle of this crowded forest, you feel like your world is full of trees. Okay? But honestly, what it's more like is this, where we are kind of at the edge of a forest. We see trees that are living their lives close to us. We can look beyond the trees that are close to us and see maybe see trees at different stages of their life, kind of like we see stars at different stages of their life. But there definitely is an edge to the forest. And again, if you kind of want to think of the fact that somebody planted that forest at some time, it kind of has the temporal component to it. Okay. But that's Olber's paradox. It says basically, since here on Earth, our nighttime skies are dark, it really supports the fact that there was a beginning to what we call, and Einstein linked space and time. There was a beginning to time and there was a beginning to space. Okay. Last slide, basically yet another thing that supports the kind of the 8 errors that I talked about earlier on last week's day. Okay? You guys don't know, but that is the last slide because you guys didn't print out my slides. Some of you didn't. Okay? That's all I have.